Hello everyone, welcome back to this class. In last class we have seen the introduction of the control system design. So in this class also we will continue. So now as already I told you about the plant, so it is very important to know the behavior of the plant in order to control the plant. So how will you model the plant? For example, that can be the first order and second order system. So you should have a in control system you should have a feel for the first order system, second order system, like that. Okay. So now we will tell you the some. We will start with the first order system. So you can see that I have taken example of a jet engine, and you can see in time domain I can write x dot plus 1 by t equal to ft by t, and t is constant basically. So when you, for example, if you consider this engine, when you put the throttle from 0 to some value, you will not get immediate thrust, right? It will take some time. So that means some kind of dynamics has been already involved in this. So that can be modeled as a first order, second order. So that is the significance of first order and second order system. So now you can see here in frequency domain you can write this transfer function as a 1 upon ts plus 1, and now I have plotted this with time. So we will go back and we'll try to take out something from this expression. So what is written here? X dot plus 1 upon t ft by, where ft is a input, you can say. Now if you take Laplace transform, see I have used the word Laplace transform, right? If you go back to the engineering mathematics class, you might have studied this like Laplace transform and Fourier transform. So Laplace transform of a function is, Laplace transform of any function is 0 to infinity f of t e to the power minus st dt, where s is sigma plus I omega. Do not confuse with the Fourier transform. The Fourier transform is minus infinity to infinity f of t e to the power plus j omega t dt. Fourier transform, right? Fourier transform of any function. So generally Fourier transform deal with e to the power j omega t, only imaginary part, right? But here you can see that in Laplace transform you have both real part and imaginary part. So you can see the Fourier transform is a part of Laplace transform if you put sigma equal to 0, right? So why s equal to both real part and sigma part? In detail I will tell you later, but here you can see, here you can see, if you have a system response like this, so it is a both oscillatory region, right? So the acceleration is coming because of this imaginary part, and you have a some kind of exponential decay, right? Here you can see exponential decay, right? That is because of real part, real negative part. If this is positive, then you will see the divergence. So try to understand the significance of this. So you go back to your mathematics class and try to revise this. And if you take the Laplace transform, you will get s into x of s plus 1 upon t into s of s into f of s by t. So you can write x of s t plus 1 f of s, right? So if you write output by input, which is 1 upon st plus 1. Clear, right? What is the Laplace transform of 1? I will give you the Laplace transform of 1 t sine cos, everything Laplace transform list I will give you. But if you put ft equal to 1, what you will get? If you put ft equal to 1, what you will get? 0 to infinity e to the power minus st dt, right? So the integral you can write e to the power minus s t by minus s from 0 to infinity. So that will be turn around 1 by s, right? So like that you can have a Laplace transform of x dot derivative of xx by f of s can be written as a 1 upon st plus 1. You agree with me, right? And how we have written that I have told you. So that is a why, if you convert from time domain to frequency domain, why this expression is coming, I am trying to explain you, and that is why I have done the some small derivation by taking the Laplace transform of this. So now you can see, if you have a t value different value, your response will be different. You can see I have given the step response. So if you take t equal to 2, you have a this response, and if you increase t, if you decrease t, you will go closer what you want actually. See this, at t equal to 1 second, your output, in ideal case your output should be 1, right? But your output is what? At t equal to 1 second, for this case 40%. Because of what? Because of this dynamics. So for example, if this t value is less, that means your system is fast, you can say. And if t value is high, you can say your system is slow, because at one time t equal to 1 you are getting 40% only. But when I say slow, then do not confuse with the delay. Delay is a different thing. That means you have deflected elevator or any control surfaces, but you are getting the time response late. But here you are getting immediately, right? So that kind of feel you should develop. And when I say unit step, what do you mean by unit step? See, there is a three type of input I have written, right? Unit step, unit ramp, unit impulse. Okay. So I will explain all three, and I will show you how why it is coming. Y equal to 1 minus e to the power minus t by t. Okay. So we'll go back. We'll take this expression. This expression is x of s f of s 1 upon ts plus 1. Okay. So now we can put x of s equal to 1 upon ts plus 1 into f of s, right? Simply fs I have taken this side. So if I will take 1, then what is the Laplace transform of 1? I have shown to you, right? 1 by s, right? And how it is coming, that also I have shown to you. So you can write 1 upon Ts plus 1 into 1 by S. And one more thing you should remember, when I have taken the Laplace transform in order to get the transfer function, I assumed initial condition 0. So after assuming initial condition 0, you can stabilize the relation between output and input. But more importantly, why initial condition are 0? Because our system is linear time invariant. That means it is not changing with a time. And Laplace transform can be applied only for a linear system. Now I will explain. When I have taken this, I have written S into S of S, right? Not something else, right? Not any initial condition you have not getting, right? I am not putting initial condition because our system is linear time invariant, and putting initial condition 0, considering linear system, in linear also linear time invariant, then only you can write a transfer function which is output by input. So do not give that this definition. If anybody asks you what is transfer function, output by input, no, output by input is efficiency also. So each and every time you have to understand why the initial condition 0, why the linear time invariant, what do you mean by this? Okay, and now you can see the significance of 1 by S. When you say unit, one transfer function means 1 by S. Okay, now we will find out the solution. So this you can write 1 upon S minus 1 upon Ts plus 1. This way you can write by breaking this partial fraction. If you solve this expression, you will get this only, right? See this. If you solve this, you will get this only, right? Ts plus 1 minus St get cancelled, this one. So if you take, see, Laplace transform is used to transform time domain to frequency domain. And what are the advantage I have given to you in the last class? And if you take the inverse, you will get back to that in time domain. So if you take the inverse, what is the inverse of 1 by S? What is the inverse? No, Laplace inverse. If you take the Laplace inverse, L inverse X of S, so Laplace transform of 1 is what? So what will be the inverse? Reverse back, right? 1. And here you will see e to the power minus t by capital T. If you go back to the Laplace transform explanation, you can get this expression also. Okay. So you should know Laplace transform of 1, Laplace transform of t. For example, like if I given you the Laplace transfer of a t, then you break with the partial integration and apply the limit, you will get something like a 1 upon S square. So Laplace transform of 1 is 1 by S and t is 1 by S square. So you can see what is the solution I am getting, 1 minus e to the power minus t by capital T. You put t equal to capital T only, same. Can you tell me the answer what you are getting? Small t equal to capital T. That means this will be value will be 1, right? So 1 minus e to the power minus 1. What is the value in calculator? Can you tell me? 0.36. So 1 minus 0.36 how much? 0.662, right? Now have a feel for this. When you t equal to 1, what is coming? 0.62, right? So that kind of feel I want to give you why this solution is coming. So understand this why is coming, right? This is why this solution is coming. 1 minus e to the power minus t by t. Meaning of unit step. Okay. Now you derive yourself with the other two, but I will give you the feel for unit ramp and unit impulse. And consider this example of aircraft. Unit step means you have given some elevator, right? For example, if you given elevator 5 degree, so 5 into 1, 5, right? So 5 step you have given, right? So that means in plot you can show this is a unit step. What is unit ramp? With time it is increasing. It is unit ramp. So unit step Laplace transform 1 by s, and in this case 1 by s square. And now the third comes, very important and little confusing, impulse. See, have you heard the word impulse in rocket, right? Suddenly on and off. So you can see, but mathematically first you will see. Let's say mathematically we will see. You have noted down, right? So unit step, unit ramp is clear, right? Now I will tell you the unit impulse. So consider this box, and in middle you have the one line. Okay, divide this line. This you consider as a minus a by 2. This you consider a by 2, and this height you can consider as a 1 by a. So what is the area? Can anybody tell me what is the area? A into 1 by a, 1 unit area, right? Now if you reduce this width, in order to make a unit area, what you will do? You will try to stretch this up, right? So if this distance a is close 0, tending to 0, then what is this height going to tending to, you can say tending to, then what is it tending to? So 1 into 0, 0. In that sense you can see it is tending to infinity. So that magnitude will go to, this is amplitude, right? Will go to infinity. That means impulse is something like that. Very small interval of time, right? So you have a feel for this. When you roll the aircraft, you generally give the aileron, right? You give the down aileron and then return back to the original position. That is how the aircraft rolls, right? For to elevator and rudder, you can have a feel for step response. For aileron, you have a feel for an impulse response. Impulse is little confusing, but I have tried to explain with this simple example why 1 and why it is going to the close to 0, then going to infinity, right? So now unit step, unit ramp and unit impulse are clear. So exam it can come, right, with the, if any transfer function is given and any input can be given, unit step, unit ramp and unit impulse, you have to find out the solution for that. So now I have tried to relate the first order system with the realistic example. Time domain I have given the definition, and then when I have converted back to the frequency domain, I have shown you the derivation, and then how this solution is coming also I told you, and what is the significance of this graph, that also I have told you. So first order system clear. So for example, in your case, if the model dynamics is not given, so you can model using first order. So you might have heard people are saying, I have modeled my sensor using first order. Now first order is clear, right? We'll go to the second order system. Here one more thing. Have you seen any kind of oscillation here? No, right? Because it is a first order system. In second order system, now the frequency and damping will come. This is a second order system. This is a spring mass system. Simple example you can consider a spring mass system. So do not worry about each and every things I will discuss with you. I will tell you what is the two parameter. One is natural frequency and another one is the damping ratio. Let's say this is the arbitrary response of any system. And why it is starting from 0? Because in transfer function, what you have assumed? 0 initial condition, right? So you have to have a feel for that. When you have assumed 0 initial condition, that is why your graph is starting from 0. Now, this is a general response is given, right? I am trying to explain this definition one by one, and then we'll go back to this spring mass system and we'll try to drive the solution, and I will tell you more about the spring mass system. So you can see when the output reaches from 0 to 50%, it is delay time, and rise time is, for example, 0 to 100% or 10 to 90% or 5 to 90%, anything you can take. So see, 0 to 100%, what is this? TR, rise time. So delay time, rise time, clear, right? For example, you have commanded pitch 5 degree, but it reaches the 2.5 degree in sub-second, right? So that will be your delay time, right? And if it reaches at a 5 degree exact, if you note down the amount of time, that will be the rise time. But you will, since you have some speed, right? So because of inertia, we will try to overshoot, right? So when here it is a maximum overshoot, right? So that time is a peak overshoot time. So 3 time I explained to you, and then settling time, that means although the system never settles, it has some 2%, 5% error, right? But you assume if you reach to the 2% of a steady state value. When I say a steady state value, that means I have commanded 5 degree, but instead I have reached to 4.888, something like that, close to 5. So within the 2% and 5% band, if you reach that time, you will note down, or you will call this a settling time. And this error is, what is 2% and 5% I am talking about, that is the steady state error. And what you have commanded 1 degree, and up to what you have gone through, that is, if you differentiate from 1, that will be the peak overshoot. Acceptable if it is less than 10% in control system design criteria. So each and every definition clear, right? So when you have a solution, you can actually derive this expression also. Why this pi by omega d is coming? Omega d is a damn natural frequency. And okay, I will tell you this. So this is a spring mass system where K is a stiffness. So K will tell you the restoring characteristics like Cm alpha, right? Try to pitch down, right? So if you try to increase the pitch up, it will try to pitch down. Inherent tendency, right? So restoring force will be provided by K. And what is C? C is a damping. For example, if you take inverted pendulum and if you disturb from the equilibrium position, it will take some time to damp. Why it is damping? Because of the air is providing the damping, right? So C. You have that kind of field for C and K. So now three parameters, right? M, C, and K. So in equation of motion, you can write what is F equal to MA, right? So MA you can write M d square by dt square, or you can write M x double dot, right? And what will be the restoring force? This external force kx minus cx dot. If you bring this side, you will have a x dot double dot plus kx plus cx dot, and you are applying some input also, right? You can write. So this you can write, okay? Or if you rearrange, you can write cx dot first before the kx, so you can write cx dot plus kx equal to f of t. So clear, right? Why this expression is coming, right? Mx, this is double dot, right? Plus cx dot plus cs equal to f of t. This is clear, right? So again take the Laplace transform. So what you will get? Double derivative s square. So ms square c x dot s plus kx 1 upon ms square plus cs plus ks. Clear, right? How it is getting, right? Now again take unit input, and if you do the same, you will get the this expression. But I will drive in the we will drive in the next class, right? Thank you so much.